Good morning, students. So today I am coming with another new chapter in software engineering. So it is software design basics. So it is very important. What do you mean by software design? So design is a meaningful representation of something which is to be built. So it can be traced to a customer's requirement at the same time assessed for quality against a set of predefined criteria for good design. A set of design concepts have evolved over the year. According to M.S. Jackson, the beginning of wisdom for a software engineer is to recognize the difference between getting a program to work and getting it right. So the definition of software designs are as diverse as design method. So according to some software engineers or computer scientists, lots of definitions we can found. So first, if we see, according to Code and Yarden, software design is the practice of taking a specification of externally observable behavior and adding details needed for actual computer system implementations, including human interaction, task management, and data management details. So according to Stephen, software design is the process of inventing and selecting programs which meet the objective of software system. So software design is also a process of transform users' requirement into some suitable form. So with the help of the programmer in software coding and implementations. For assessing user requirements and SRS software requirements specification document is created, whereas for coding and implementation there is a need of more specific and detailed requirements in software terms. So the output of this process can directly be used into implementations and programming language. So software design is the first step in SDLC, software design life cycle, which moves the concentration from problem domain to solution domain. So software design levels. So software design yields three levels. One is architectural design, next high level design, and third one is detailed design. So what is architectural design? The architectural design is the highest abstract versions of the system. So it identifies the software as a system with many components interacting with each other. So at this level, the designer get the idea of proposed solution domain or proposed system. Next, high level design. The high level design breaks the single entity multiple components concept of architectural design into less abstract view of subsystems and modules and depicts their interaction with each other. So high level design focused on how the system along with all of its components can be implemented in the forms of modules. Next, if we see detailed design, so detailed design deals with the implementation part, what is seen as a system and its subsystem in previous two designs. So it is more detailed towards modules and their implementations. It defines logical structure of its module and the interface to communicate with other modules. So Now, if we see the term modular, what is modularization? Modularization is a technique to divide a software system into multiple discrete and independent modules, which are expected to be capable of carrying out tasks independently. So this module may work as basis construct or basic building blocks for the entire software. So designers tend to design modules such that they can be executed or compiled separately and independently. So modular design unintentionally follows the rule of divide and conquer problem solving strategy. So this is because there are many other benefits attached with modular design of a software. So advantage of modularization: smaller components are easier to maintain. Program can be divided based on functional aspects. Desired level of abstraction can be brought into program. Component with high cohesion can be reused again, and concurrent execution can be made possible. Desired from security aspect. Again, if we see concurrency, the term concurrency. So back in time, all software meant to be executed sequentially. By sequential execution, we means that the coded instruction will execute one after another, implying only one portion of program being activated at the given time. But software has a multiple modules, then only one of all modules can be found active at the time of execution. In software design, concurrency is implemented by splitting the software into multiple independent units of executions like modules and executing them in parallel. In other words, concurrency provides capability to the software to execute more than one part of code in parallel to each other. So now another important term, coupling and cohesion. Before going to this, why we discuss about design objective. So software design has some objective. First one is correctness. So correctness, the design of a system is correct if system built precisely according to the design satisfies the requirement of the system. Number 2, verifiability. Design should be correct and it should be verified for correctness. Number 3, completeness. So completeness requires that all the different components of design should be verified. Next, traceability. Traceability is an important property that can get design verification. Next, efficiency. Efficiency of any system is concerned with proper use of resources by the system. Finally, simplicity. Simplicity is the perhaps the most important quality criteria of software system. So if we see next, we see the term coupling and cohesion, which is important in software design concept. So when a software program is modularized, tasks are divided into several modules based on some characteristics. So as we know, modules are set of instructions put together in order to achieve some task. They are through considered as a single entity but may refer to each other to work together. There are some measures by which the quality of designs of modules and their interactions among them can be measured. So these measures are called coupling and cohesion. So coupling and cohesion is nothing but it's the measures by which quality of designs of modules and their interactions among them can be measured. So what do you mean by cohesion? Cohesion is a measure which defines the degree of interdependability within elements of a module. So the greater the cohesion, the better is program design. So cohesion means it defines the degree of interdependability among within the elements of a module. So it is very important. There are 7 types of cohesion. We have 7 types of cohesion, which are you can see one by one. So that is number 1, coincidental cohesion. So coincidental cohesion means it is unplanned and random cohesion, so which might be a result of breaking a program into smaller modules for the sake of modularizations. Because it is unplanned, it may serve confusion to the programmer and generally not accepted. Next, logical cohesion. When logically categorized elements are put together into a module, it is called logical cohesion. Next, temporal cohesion. When elements of module are organized such that they are processed at a similar point of time, it is known as temporal cohesion. Next, procedural cohesion. Procedural cohesion, when elements of module are grouped together which are executed sequentially in order to perform tasks, it is known as procedural cohesion. Next, communicational cohesion. When elements of module are grouped together which are executed sequentially and work on same data information, it is called communicational cohesion. And next, sequential cohesion. When elements of module are grouped because the output of one element serves as input to another, so on, it is called sequential cohesion. And finally, functional cohesion. It is considered to be highest degree of cohesion. It is the highly expected elements of module in function cohesions are grouped because they are all contribute to a single well-defined function. It can also be reused. So this is about the cohesion. Now, if we see coupling. So coupling is a measure that defines the level of interdependability among modules of a program. So the coupling between two modules indicates the degree of interdependence between them. So if two modules interchange large amount of data, then they are highly interdependent. So the degree of coupling between two modules depends on their interface complexity. So the interface complexity is basically determined by the number of types of parameters that are interchanged while invoking the function of the module. So highly coupled, if we say some highly coupled, when the modules are highly dependent on each other, they are known as highly coupled. And loosely coupled, when the modules are depend on each other but the interconnection among them is weak, and it is called loosely coupled. And uncoupled means when the different modules have no interconnections among them, is known as uncoupled module. So coupling tells at what level of modules interact with each other. So the lower coupling is better for the software design. So there are 5 levels of coupling, namely content coupling, when a module can directly access or modify or refer the content of another module is called content level coupling. Then common coupling, when multiple modules have read the write access to some global data, it is called common or global coupling. Next, control coupling, two modules are called control couple if one of them decides the function of another module or changes its flow of executions. Next, stem coupling, when multiple modules shares common data structure and works on different parts of it is called stem coupling. And finally, data coupling. Data coupling is when two modules interact with each other by means of passing data parameter. If a module passes data structure as parameter, then receiving module should use all its component. So ideally, no coupling is considered to be the best. That means high coupling among modules not only makes the design difficult to understand and maintain, but also increase development effort, as the module having high coupling cannot be developed independently by different team members. So module having high coupling are difficult to implement and debug. So we always want lose low coupling. Now if we see relation between coupling and cohesion, then a software engineer must design the module with the goal of high cohesion and low coupling. It is important to remember that a software engineer must design the modules with the goal of high cohesion and low coupling. Now, if we see the design verifications, the output of software design process is design documentation, pseudocodes, detailed logic diagrams, process diagrams, and detailed description of functional and non-functional requirements. So the next phase, which is the implementation of software, depends on our output mentioned above. So now software analysis and design tool. If we see, software analysis and design includes all activities which help the transformations of requirement specification into implementations. A requirement specification especially all functional and non-functional expectations from the software. So software analysis and design is the intermediate stage which help human readable requirements to be transformed into actual code. So there are lots of tools in software analysis and design tools. So one is data flow diagram, DFD. So DFD, data flow diagram, is a graphical representation of flow of data in an information system. So it is capable of depicting incoming data flow and outgoing data flow and stored data. So the DFD does not mention anything about how data flows through the system. There are prominent differences between DFD and flowchart. So the flowchart depicts the flow of control in program modules, but DFD depicts flow of data in the system at the various level. It does not contain any control or branch elements. So type of DFD. There are basically two types of DFD, data flow diagrams. One is logical DFD and another is physical DFD. So logical DFD, this type of DFD concentrates on the system process and flow of data in the system. For example, in a banking software system, how data is moved between different entities. And in physical DFD, this type of DFD shows how the data flow is actually implemented in the system. It is more specific and close to the implementations. So now if we see DFD components, so DFD can represent source, destination, storage and flow of data using following set of components. So if we see, this is entity, so it is rectangle shape entity, and process is circle shape. Data storage is one side open rectangle, and data flow is in this arrays. So car in this way, if we data flow in this means flow from this to this, and this way from this to this. So entities are source and destination of information data. So it is source and destination. So entities are represented by rectangle with their respective names. Next, process. So process, the activities and actions taken on the data are represented by a circle or round edge rectangle. So it is process. Process means which is action taking place on data. Next, data storage. There are two variants of data storage. It can be either represent a rectangle with absence of one both smaller side, or as open side rectangle with only one side missing. So this is data storage. And data flow, movement of data in this way. Movement of data by pointing arrows. Data movement is shown from base of arrows to the source towards head of the arrows at the as destination. So level of DFD. There are different level of DFD we have. So 0 level, but level 0, highest abstraction level of DFD is known as level 0 DFD, which depicts the entire information system as one diagram concealing all the underlying details. So level 0 DFD is also known as context level diagram. So context level DFD, that is this system, online shopping system and customer order on online shopping system and it is delivered. This is 0 level DFD, just abstraction level, highest abstraction. We cannot see others, just two entities. One is online shopping system and other is customer. And data flow occurs in both directions. So level 1, the 0 level DFD is broken into more specific. So level 1 DFD depicts basic module in the system and flow of data among various modules. So level 1 DFD also mentions basic processes and source of information. Just if we see the level 1 level DFD, first level DFD, then we see here customer is storage, customer data. These are entities, account, stores, sales, and customer again another entity. So customer, order, sales, delivery, and sales again depend on the process, order, processing. So sales process order, and order process gives order to sales, and stores again issue them directly in both way communications with the process order processing. Then customer data stored, verify in this storage area, and above accounts again financial verification is done, the accounts entity with the process order processing. So in this way we have first level DFD. So level 2, at this level DFD shows how data flows inside the module mentioned in one level. So in this again if we go details inside the modules of first level DFD, then we have second level DFD. So higher level DFD can transform into more specific lower level DFDs with deeper level of understanding unless the desired level of specification is achieved. So in this way we have DFDs. Next, structure chart. So structure chart is a chart derived from data flow diagram DFD. It represents the system in more details than DFD. It breaks down the entire system into lowest functional modules, describe functions, sub-functions for each module of the system to a greater detail than DFD. So structure chart represents hierarchical structure of modules at each layer of specific task is performed. So here symbols and construction of structures at module. So module, it represents processor or subroutine or task, a control module branch of more than one submodule. Next, if we see this control module and this is submodules, if we divide again this control module controls this submodule. So conditions, it is represented by small diamond at the base of module. So it depicts the control module can select any sub routines based on some condition. So this is condition. So based on this condition, if condition satisfied, then it takes this module and other control, and otherwise this module. Jump. So the arrow is shown pointing inside the module, depict that control will jump in the module of submodule. So the control is jump to this module, from this module to this module. Then this is we give in this way. Then loop. So a curved arrow represents loop in the module. All submodules covered by loop repeated execution of module. So this is loop. That means this repeatedly executing. So data flow, a direct arrow with empty circle at the end represented data flow. In this way, data flow levels from module, this module to this module. This is control module, this is submodules. Again, flow control. So a directed arrow with fill circle at the end represent flow control. Represent control flow control. So this is data flow, that means it is empty, and if we give this fill up, then it is flow control flow. This is not needed. So today I stop my class. Thank you.